Welcome back to another explainer. Today, we're unpacking something genuinely fascinating, a red team analysis of the Veil dataset using a methodology called VEILBreaker V1. Think of this whole process like a high-stakes forensic investigation. Imagine you're a detective. You show up at a crime scene, but instead of finding your suspect, you only find their shadow cast against a wall. You literally can't see their face, you don't know their name, but just by measuring the exact geometry of that shadow, you can deduce their height, their posture, maybe even their build. Well, that's exactly what we're doing today, but with raw data. Okay, let's dive into this.
Just to give you a quick roadmap of where we're headed, we'll start with the core puzzle, which is the 4096 scalar mystery. Then we'll look at why perfect reconstruction is statistically impossible. After that, we'll break down the actual red team audit logic, trace how the VEILBreaker feature extractor evolved, and wrap up with the final results and verdict.
So, Section 1, the 4096 scalar mystery.
Imagine you're handed a digital file. You crack it open, and all you see is a single, one-dimensional array. Inside, exactly 4,096 scalar values, just a list of numbers. That is your entire universe of information for this challenge. Let that sink in for a second. We're talking zero accompanying manuals, absolutely no labels, no metadata whatsoever, just 4,096 isolated data points staring back at you. How do you even begin to make sense of that?
To really appreciate the sheer difficulty of this, think about everything we do not know here. The original data table, completely unknown. The encoder algorithm that compressed the data, totally hidden from us. We literally have no idea what the original dimensionality was, what the features were named, or if they were categorical, numerical, or text. The scales, the underlying semantics, even the specific downstream task these values are supposed to solve, it's all completely unstated. I mean, it's basically a data scientist's worst nightmare, right? At first glance, this feels like total defeat. But here's the thing. In the world of red team auditing, a massive lack of context isn't a dead end. It's actually an invitation to start reverse engineering.
Moving on to Section 2, why reconstruction is impossible.
Now, what's really interesting about this is why trying to perfectly rebuild the original room from scratch is just a fool's errand. It all boils down to one foundational equation, z equals e of x. In our scenario, z represents those 4,096 compressed scalar values, the output. E represents our completely unknown encoder, and x is the highly mysterious original dataset. Mathematically speaking, because both x and e are entirely unknown, this problem is statistically non-identifiable. And what does that mean in plain English? Well, it means that infinitely many different hidden tables passed through infinitely many different encoders could produce the exact same scalar stream z. Without paired training examples, you simply cannot reverse engineer the true original table.
Because of that mathematical reality, VEILBreaker makes a massive pivot. We completely abandon the fantasy of full reconstruction. As we just learned, the original dataset and encoder are hidden forever, so claiming to perfectly recover them, that would just be intellectually dishonest. Instead, VEILBreaker targets partial signal extraction. And this is highly achievable. If we can't have the original object, we're going to carefully, rigorously measure its shadow. The entire focus shifts to mapping whatever geometric relationships and data structures actually survived that compression process.
That brings us to Section 3, the red team audit logic.
The absolute core logic of a red team audit is shifting your perspective. You have to stop looking at this scalar stream as a broken puzzle and start treating it as an exposed attack surface. Usually the defense of compressive latents claims that reducing dimensionality destroys invertibility, supposedly making it safe. But we completely reverse that argument. Think about it. If this scalar latent stream is still useful for some downstream task, then some task-aligned structure absolutely must have survived the compression. Our job is simply to poke and prod at that surface to see what held up. We're looking for preserved rank order, local density, data gaps, tail behaviors, and nonlinear curvature. We analyze magnitudes and asymmetry and spectral diversity. And, crucial point here, we have to interpret all of these results with intense caution and statistical honesty.
And this brilliantly illustrates exactly how we interrogate that shadow using 12 distinct diagnostic families, without getting bogged down in the mathematical minutiae. It's a comprehensive gauntlet. We've got distribution diagnostics, Gaussian null comparisons, Vosterstein-1 signatures, global rank, gap and spacing, local density, tail and outlier analysis, nonlinear curvature, radial magnitude, and positive tail asymmetry. On top of that, we apply spectral diagnostics, things like singular values, effective rank, and entropy, alongside rigorous contract tests to ensure finite deterministic behavior like permutation equivariance and checking for nan or inf values. By running those 4,096 scalars through this massive gauntlet, we start mapping the precise contours of the hidden data.
Let's look at Section 4, Evolving the VEILBreaker Extractor. The development of this tool actually started with a head-to-head comparison between two early models, D4 and D8. Now, D4 was highly elegant. It extracted just 4 features from the scalars: the normalized value, the rank, a logit rank score, and local density. Super simple, remarkably stable, highly interpretable, and critically, it was tie-away and permutation equivalent. Then they built D8, basically throwing in more mathematical transformations just to double the dimensions. But here's a massive lesson in data science. More dimensions absolutely do not automatically mean more information. The audit proved that D8 just created a bunch of redundancy and artificial complexity without adding any true predictive value. Useful, non-redundant features matter so much more than sheer volume.
Let's move to and see how this builds across the project's timeline. Step 1 was that elegant D4 baseline we just talked about. From there, the team evolved to V4. They carefully expanded to 8 features, pulling in zets, signed square, sin, cos, and tan, while keeping that core rank, density, and clipped logit. It was a much more mature expansion than that initial D8 experiment. Finally, through some really rigorous testing, they arrived at step 3, V5B Lite. This is the final, highly optimized 10-dimensional model designed specifically for partial signal extraction.
So what exactly made V5B Lite the ultimate winner here? Well, it took that really solid 8-feature core from V4 and added 2 highly specific, non-redundant mathematical tools. First up, it added a feature called f-log-abs. This was specifically engineered to capture compressed radial magnitude that the earlier models were completely missing. Second, it added f-express-pos, which was explicitly designed to capture positive tail asymmetry, a really interesting structural quirk they detected during the audit phase. By combining those 2 surgical features with the V4 core, the extractor reached a final output dimensionality of exactly 10.
But you know, great feature engineering isn't just about what you cram in. It's about what you have the discipline to take out. To prevent that artificial complexity we saw back in the D8 days, the team actively pruned the model. For instance, they dropped F-quantile because the diagnostics clearly showed it was completely redundant with the existing rank feature. They also tossed out the error function feature, FERF, because ablation testing proved it actually had a negative contribution to the model stability. Grounding your theory in practical, ruthless pruning is what actually makes a model robust.
And finally, Section 5, Final Results in Verdict. So the crucial point is how the final model actually performed. The V5B Lite extractor successfully processed all 4,096 rows into a perfectly aligned 4,096 by 10 matrix. It crushed the validation, passing 11 out of 11 strict contract tests and 10 out of 10 permutation tests. It achieved an effective rank of 4.6649 and a solid entropy score of 1.5401. Because of these rock-solid metrics, the final verdict for the VEILBreaker extractor was a resounding promotion candidate. It did exactly what it set out to do. Which brings us to this final, somewhat haunting thought straight from the project's documentation. VEILBreaker does not recover the hidden table. It maps the geometry of the scalar shadow. The table remains hidden, but the geometry does not disappear completely. I absolutely love that phrasing. It perfectly encapsulates the profound nature of partial signal extraction. The table remains hidden, but the geometry does not disappear completely. It really forces us to ask, in an age of massive opaque data compression, is any information ever truly hidden? Thank you so much for joining me on this explainer today, and keep questioning the data.